But wait, there's more. Because as if this wasn't complicated enough, right? If you were kind of doing some critical thinking, maybe you realized we didn't actually answer whether any particular groups were better or worse for treating Parkinson's than the others, right? How do we know which treatments worked better or worse than the others? We didn't answer that question. So to do that, we have to do something called multiple comparisons. So why do we need multiple comparisons? Well, if we get a significant F value from ANOVA, this only tells us that the overall null hypothesis is probably false. So the overall null hypothesis being that all our means are the same. So this tells us that two or more means differ from each other. It does not tell us which means in particular are different from which other means. It just says there's a difference somewhere among your means. It doesn't tell us which ones are different. And if you're trying to choose a particular treatment, it might be important to know which one is the one that works best, right? So multiple comparisons allow us to investigate our hypotheses about the means of individual groups or sets of groups. It allows us to actually do that comparison. The overall ANOVA is saying, yep, there's a difference somewhere. We want to know with multiple comparisons, okay, where is the difference, or is there more than one difference? So we have two types of comparisons. We can do a priori, which means that we plan to compare specific groups against each other before we ever collected our data. Or we can do post-hoc comparisons, which is by and large, definitely the more common type of comparison that you'll see. You will very often see post-hoc tests, not so often with a priori. Okay, so post-hoc means that we decided to test for differences between our groups after we already collected our data. So this term right here, pairwise comparisons, this just means comparing one group against another. We take a pair of groups and we compare them, right? So that's all that it means, pairwise comparisons. Now the number of comparisons that we have to do depends on how many groups we have in our study. If we have 3 groups, we compare 3 times. We compare A to B, B to C, and A to C, right? Because if we did C to B, well, that's the same as doing B to C, and if we did C to A, that's the same as A to C, right? If we have 4 groups, it gets a little messier. We have to do A to B, A to C, A to D. Then we don't do B to A because that's the same as A to B, but we have to do B to C and B to D. And then C, we don't need to do C to A because that's already here. We don't need to do C to B, that's already here. We do still need to do C to D. So now we're up to 1, 2, 3, 4, 5, 6 comparisons. So it very quickly gets kind of out of hand, right? So then if we have 5 groups, we would actually end up having to do 10 pairwise comparisons. If we have 6 groups, we have to do 15 comparisons. If we have 12 groups, we have to do 66 different comparisons in order to compare all of our different groups against each other. Now, the thing is, we talked about type 1 error, and that's the chance of falsely finding an effect when there really isn't one, right? So we set our alpha level at 0.05. And what that means is that we're okay with there being a 5% chance that we say we found a significant effect when really there's not one there. We're saying we're okay with 5% chance of being wrong here, right? Now, if when we do one test we have 5% chance, and we do another test and we have 5% chance, and we do 10 tests, how many, like what are the chances that we would make a mistake? So that chance of making that kind of mistake, a type 1 error, goes up depending on how many of these tests we're running at the same time. So this is called the family-wise error rate. When we're just doing one test, we have 0.05 chance of making it a mistake. But then that chance goes up and up and up and up as we have more and more comparisons. All right? So in order to control for that, then we have to use specific tests, right? And this is post-hoc testing. So if more than 3 groups are involved in the study and we're doing post-hoc testing, then the chances of finding some comparisons that are significant when really they shouldn't be, when it's a type 1 error, goes up. This means there's an increase in type 1 error across the family of all possible comparisons of the means. So we tend to say that the family-wise error rate increases. So if you think, oh, I'm doing 6 comparisons because I have 4 groups, that's a family of comparisons. The error rate across all 6 of those tests, that family of tests, is higher than if you were just doing one test. So the family-wise error rate has gone up. We need to control for this, and we do that by using special procedures when we do multiple comparisons. So post-hoc tests. Sometimes, actually often, hypotheses are only arrived at after we collect the data. So for example, after you collect your data and you do an ANOVA, and you see there's a significant difference, you might think, oh, maybe it's because of this. And then you have to check that. You have to test that hypothesis. Sometimes investigators fish for significant effects where they just kind of want to test everything. Not exactly great science, but it does happen. Regardless, either way, you need to select a post-hoc test to try to control for that family-wise error rate. So here I'm just going to talk about a couple of the most common, there are tons of them, but some of the most common post-hoc tests that you'll see. So one of the very most common ones is Fisher's LSD, which stands for least significant difference. You can use Fisher's LSD when you're doing an a priori, so planned comparisons, no matter how many groups you have. Of course, most of the time we're doing post-hoc tests. So for post-hoc tests, it's recommended that you only use Fisher's when you have 3 groups. So if you have more than 3 groups, don't use Fisher's, use a different test, and we'll talk about what would be a better test. Also, with Fisher's, when you're doing post-hoc testing, you only run Fisher's if your overall ANOVA comes out as significant. If your overall ANOVA isn't significant, do not run Fisher's, right? Don't go fishing for a significant effect. You won't find anything. And Fisher's is the most powerful of the post-hoc tests that we're going to be talking about. And you'll hear people, they call it the most liberal test. And the reason it's called that is because it's the one that if you use it, you're the most likely to find a significant effect. That's because it has a lot of power behind it, so it can detect even very small differences. And so some people think, that's not, maybe we want to be a little more careful. And so they wouldn't want to use such a liberal test. They want to use a more conservative test. But if you're really trying to find something, like you want the most powerful test you can use, then Fisher's is the one. So in this case, because we have 4 groups, and I said don't use it with more than 4 groups, let's just assume that we were doing this based on a priori, right? Just so I can demonstrate what it'll look like when you do it. So you would do a Fisher's LSD test in SPSS by going to Analyze, General Linear Model, Univariate, just like before. You put your dependent variable and your factor into the boxes. Then you select the options button. And we selected that before to check for different things, right? Now you're going to take the factor in the factor box and move it over to the display means for box. There's a box underneath that you tick called compare main effects, and we're going to do all of this in class and you're going to see it live. So don't worry if you're like, this means nothing to me right now. I'm just going through it so that later on, if you want to go back and review after you've seen it in action, you have it. So then a little box under the display means box will come live, and you would check that, the compare main effects, and then you'll see that there are several options, and you scroll down, you select the drop down and select LSD, none. This is what you're going to see. And this is the kind of thing I'm talking about when I say that SPSS gives you 50 numbers when all you need is 3 or so. Right? So how the heck do you read this table? Because there's a lot of junk in it. So the first thing to notice is that we have our, let's undo that. We have our 4 different treatment groups here, right? So really what I usually tell people is ignore all of this. We don't care. What we want to focus on is comparing, let me delete these for now. We want to compare this with this, okay? So if we want to know, was there a significant difference between the no therapy control group and the placebo control group, we come over and look at this p-value. If p is less than 0.05, which it obviously is in this case, then yes, there is a significant difference. Actually, let's not put it right there. There is a significant difference between no therapy and placebo. Next, we want to look at no therapy and control it against conventional therapy. Look at this p-value over here. We see it's, again, less than 0.05. That means that, yep, there is a significant difference between no therapy and conventional therapy. Finally, we want to compare no therapy with new age therapy. Come look at the p-value over here, also significant. Yes, there's a significant difference between no therapy and new age therapy. Okay, so we're reading straight across. Whoops, leave those out. All right, so no therapy and placebo we see here. No therapy with conventional therapy is there. No therapy with new age is there. So next, let's come down to the next box. We're going to compare placebo this time. Now, we don't need to do the first one, placebo versus no therapy, because that's the same as doing placebo versus no therapy right here. Oh, that's really hard to read. There we go. Right? We already compared no therapy with placebo, so there's no point in comparing placebo with no therapy. It's the same, it's just said the other way around. So we're just going to skip that one. Now let's compare placebo with conventional, and we want to look here, and that is significant. There is a significant difference between placebo and conventional therapy. Next, let's compare placebo with new age therapy. Right here, 0.461. That is most definitely not less than 0.05, so it is not significant. Let's do a big mark right here. Placebo control, not significantly different from new age therapy. Interesting. Now let's jump out in here. Conventional therapy. Well, we already compared conventional therapy with no therapy up here, so we don't need to read that one. We already compared conventional therapy and placebo right there. Don't need to read that one. So these are out. The only thing left to read is conventional therapy with new age therapy. And we see, yes, it is significant. So there is a significant difference between conventional therapy and new age therapy. Now, once we get down here, we've already compared new age with no therapy up here. We've already compared it against placebo in here. Already compared it against conventional in here. So we don't need any of this. So if we cross out all the stuff we didn't need, right? We didn't need any of this information. You see what I mean? The SPSS gives us a ton of stuff when we only need a few things. This is really hard to read. Let's make that yellow. There we go. So this is how you're actually going to read your multiple comparisons boxes, regardless of if we're doing Fisher's or one of the other post-hocs that we'll talk about. Oh, so let me erase a bunch of this stuff because you'll see that I actually had animations showing all the different things to look at. So how do we report these findings? We would say Fisher's LSD test comparisons revealed that the 3 therapy groups were significantly improved compared with the no therapy group, and that p-value was less than 0.001. And that's because all 3, the placebo, conventional therapy, and new age therapy, all had their p-values of 0.000 when compared to no therapy. So we would just say that all of them were p less than 0.001. Now the conventional therapy group was significantly improved, or significantly better, compared with the placebo control, p equals 0.001. So this time it wasn't labeled as 000, it was actually 001. So we say equals 0.001. And it was significantly better than the new age therapy group, and that was p equals 0.004. Finally, the new age therapy group was not significantly different, not significant because this p-value is over 0.05. So it was not significantly different from the placebo group. So new age therapy was essentially the same as placebo. And we see that p equals 0.461. Now you may be thinking, okay, I see where the significant comes from. That comes from if this is less than or greater than 0.05. But how do we know it was improved, right? How do we know these were improved compared to that? Well, that comes from looking at our means. This is the biggest mean, right? This is the highest. So if it's significant against this one, that means it's significantly, which one's higher? This one, so it's significantly better than that one. This one's higher, so it's significantly better than that one. This one's higher, so it's significantly better than that one. This one, since it's higher than both of these, we'd say is significantly higher than both of those, or significantly better, significantly improved mobility compared to those two. And a way of illustrating that on our graph, you'll see down here we have a legend where we can show where we're comparing the groups, right? So this group was significant at the less than 0.01, significant all by itself compared to the other 3. Now these two were significant at that same level. These two were significant at the 0.01 level. Now a couple other post-hoc tests. There's Tukey, honestly significant difference, the HSD, that's very common. Tukey's kind of a middle of the road test, and you want to use it when we have more than 3 conditions. It compares many pairs of means while controlling for the family-wise error rate. And apart from Fisher's, it's also one of the most powerful. So it's one of the most liberal tests. You're more likely to find a significant difference. Sheffy's is another one that you may see. Sheffy's is one of the most conservative tests, so it's least powerful. So this one is really good if you want to be extra careful and make sure you're definitely protecting against type 1 errors. If you definitely are like, I really don't want to make the mistake of saying I have a significant effect when I don't, then Sheffey's a good choice. Now this one you will see very often, the Bonferroni test. It sounds like rice-a-roni or something, right? So Bonferroni, you take your significance level, your alpha level, and you simply divide it by the number of tests that you did. And this gives you a new comparison level. So alpha divided by the number of tests you did. So for example, if we did 5 tests, then we take our regular alpha level of 0.05 and we divide by 5 and we get 0.01. This means that every test we do, we're comparing against this new level. Now 0.05 is not going to cut it. Now we're comparing against 0.01. But SPSS has a way of working this out behind the scenes, so we don't have to worry about it. You tell it Bonferroni, and it will give you a number, and then we're still comparing it against 0.05 of what we see, because SPSS takes care of it behind the scenes. So we'll see that in class, in action. In this class, Bonferroni, always an okay choice with me. Okay, so if you're trying to decide which one, and you're like, I don't remember which one is only for 3 groups or not for 3 groups, just use Bonferroni. I'm always good with Bonferroni. Now here's the final, which test do I use? Like I said, always use Bonferroni, but if you're trying to, kind of follow the rules, and I will say these rules differ a lot depending on who you ask or what book you read, but here are some of the rules that I was taught. This is what I'm going to teach you. If you're doing a priori tests were planned ahead of time, use Fisher's LSD. If you're doing post-hoc and you have 3 conditions, use protected, so use Fisher's LSD again, if you have 3 conditions. If you have more than 3 conditions, use Tukey or Bonferroni. Use Tukey because it's nice middle of the road, or use Bonferroni because, I don't know, it's just a very common one and it's a pretty safe one. If you have more than 3 conditions and you want that extra protection against type 1 errors, if you're like, I really don't want to make that kind of mistake, use Sheffey. It's the most conservative.